Okay, I'm Luca, and I will talk about compositional verification of Stigmergic collective systems. Let's start by giving you an idea of what I mean by this definition. Essentially, we are interested in collections of agents that interact with each other, and by we, I don't mean just as computer scientists, but increasingly an increasing number of researchers across many different research areas are interested in describing their systems in an agent-based fashion. And one interesting feature across these collective systems is that these interactions and the feedback loops that this interaction may originate can lead to the emergence of collective properties and features. Of course, reasoning about this kind of emergent behavior is pretty hard, and model checking may be a solution to that, to help reasoning about this stuff. For sure, it has some benefits because it provides procedures to reason about, to prove about, arbitrary temporal properties about these systems. And it's also a fully automated technique or set of techniques, so they usually do not require human intervention as part of the analysis process. But of course, they still require a consistent amount of expertise from the user, who has to build the model and specify the properties that must be verified. And of course, the state space explosion is another potential issue with model checking, because as you know, the number of agents increases, so does the potential number of potential interactions, and we all know that this can blow up pretty quickly. So what we are trying to do is to fight these drawbacks of that come with model checking, and so what we have is a high-level language called labs to concisely specify the systems that we're interested in checking and the properties of interest. We also focus on some very high-level attribute-based interaction mechanisms, and this is where the term Stigmergic will come in. On the analysis side, we are interested in reusing existing technologies that can, so that we can quickly build prototype tools that exploit existing and mature algorithms based on different approaches. In this work, for instance, we use CADP, which offers model checking and compositional verification tools right out of the box. So more specifically, we will encode these systems specified in labs into parallel programs into the LNT specification language. We will then provide a compositional verification workflow to verify such programs. And to speed this compositional verification workflow, we will rely on a sound value analysis that will prune the state spaces of agents in an over-approximating way, and this will help with the verification performance. So let's quickly talk about how this language looks like. So here we have a simple example that is a Baldi election system. So usually you have n nodes, and each node advertises itself as a leader. But as soon as someone with a lower ID comes up and advertises itself, the agents with higher IDs get out of the race. And intuitively, at the end, only the agent with the lowest ID in the system will remain in the run and will be elected as a leader. How we specify this in labs is by having the agents write their ID into a special kind of variable, which we call a Stigmergic variable, and is this leader at line 11 and 12. Here we are saying, look, if the leader is greater than or equal than my own ID, then assign my ID to leader, and then go back and do this again. And this is not a conditional, it's actually a guard, so the agent will block until this condition is true. What happens in the background is that the agents will, after they assign a value to this variable, they will exchange messages with their own values for this variable, and there will be some kind of, let's say, a consensus mechanism where values that are newer will overwrite values that are older. I don't want to get into the details, but as you can imagine, this approach can quickly lead to very big state spaces, even with a low number of agents, because these messages that are exchanged are asynchronous, and of course there is a comparison between timestamps going on, and so on and so forth. So, but I mean, intuitively, the idea is that when they do that, they should converge to a situation where every agent has 0 as the leader, either because they assign it themselves, so the agent with ID 0, or because they receive this message from some other agent. Further complicating things is the fact that we can potentially restrict how this messaging happens by means of predicates on the state of the sender and the receiver. In this particular case, as you can see at line 5, the predicate is true, so agents may always communicate with each other, but this can be customized by the user to model the specific aspects of their system. So, I mean, this is an example of what could happen when you put 3 nodes and let them run. So the simplest thing that can happen is that this agent 0 immediately assigns leader 0 to leader, and then immediately communicates, spreads this value to everyone else, and then we get to the, let's say, end state in a sense. But I mean, there are many other interleavings that might happen in between, but intuitively, the idea is that when at some point you end up in that state on the far right, and then you just, I mean, the only agent will be the 0 agent that will just update leader and so on. Yeah?
On the black arcs, should we just assume that basically all agents communicate with each other?
Yeah, a black arc is either an agent making a move, so for instance from here to here, or an agent sending a message to everyone that can receive it. But yeah, I mean, the idea is that when an agent does send a message, everyone that is allowed to receive it will receive it. That's our assumption. But yeah, but this is just in this case, because in general, if the predicate is more complex, maybe some agents are not reachable in that specific moment. Okay, so it's so for instance, a property that we could verify here is that along every fair execution of this system, there are infinitely many states where every node has 0 as the leader. Okay, so something like that. And so our question is, how do we take a system like the one in the previous slide and verify a property like this against that? So the general idea is expressed in this workflow. So we take our specification and turn it into an LNT program. So which is an LNT is a system description language. And at the same time, we take the property and we turn it into an MCL query. MCL is essentially a machine-readable implementation of the alternation-free mu calculus. So it's a branching time logic, it's fairly expressive, and allows also to have data passing between, like, you can gather data from transitions and store it and reuse it in your properties. So it's rather expressive. And then when we have these two elements, we write a script that specifies the compositional verification task. So we will generate the state space of the LNT program in a compositional fashion, and then we will verify our property against this state space, okay? So, I mean, before we go forward, I'll give a very quick crash course in what LNT does. In an LNT program, you have processes that communicate over gates. So you can either send some values over a gate, G in this case, or you can receive some values from a gate and bind those values to a certain number of variables. And additionally, you may specify a predicate that says, okay, I want to receive some values, but these values must satisfy these predicates. Otherwise, this action will block. So how do you put these together? So suppose you have a process that is willing to send and a process that is willing to receive. The general parallel composition operator is this one. So you have n processes. Each process has a synchronization set, so a set of gates that he has to synchronize upon. And in a process such as this, all processes which have some gate G in their synchronization set must synchronize over it. So by default, this language supports multi-party synchronization, not just one-to-one rendezvous. And then, of course, like these processes may be defined by means of, it's a generic programming language. You have loops. Also, you have some process algebraic stuff like non-deterministic choice between two behaviors, and so on and so forth. Conditional, guards, you name it. So, what do we do is, so the first step, yeah. Okay. Sorry, yeah.
Yeah, I just want to make sure I understand. So these events are really synchronous. There's no like sending of an event, sitting in a buffer somewhere and being received later.
That's right. Yeah. When the send happens, it's a rendezvous. It's, the sender and the receivers, they handshake and the values get bound at every process according to this, corresponding variables.
And is it the case that everybody that's listening on this receive event must receive it? Everybody has to participate?
Yeah, if you're listening, but at that moment you're not willing to receive, you're blocking everybody else.
Okay.
So, yeah. Yeah, it's okay. So, in fact, so what we do is that we take our system in labs and we encode it, and we encode every agent as a separate LNT process which has this structure. So, you first initialize the initial state, and then you have a loop where the agent may either make a move, so perform a statement, essentially, or wait for another agent to make its move. So you preserve, the interleaving semantics and you don't overlap with each other. Or you can send a message if it's available to you. Or you may react to a message that is being sent by someone else. And then you just loop over this choice over and over again. And here we have, so the system will be a parallel composition of agents such as this, plus some helper processes that store some additional information, such as the timestamps that I was mentioning that are related to the variables. And then we have, again, we will use multi-party synchronizations here to resolve the choices of the agent. So at every step, one agent will say, I want to make a move, and everybody else will synchronize and say, okay, you're making the move for this time, and so on and so forth. Or otherwise, I want to send a message, and all the other agents will receive and react to the message according to the semantics of labs. Okay, we have our LNT program like this, and it's a composition of processes, and now we want to generate the state space of such a program to perform model checking, right? And we will do it in a compositional way. In general, the idea is that of any compositional approach such as this, is that you want to generate the transition system of the whole process, of the whole composite process, as a function of the transition systems of its components. Okay? So in our work, we are using one of the potential strategies to do that. It's not the only one, but we found it works pretty well in practice for this kind of programs. And this is called root leaf reduction, modulo some bisimulation relation R. The idea is that we start and we generate the transition systems for every process in our program. Then we minimize those transition systems modulo R. At this point, so we have n transition systems, and we can now compose them to generate the transition system of the original overall system. Okay, so we simply take our system and replace, every occurrence of a process by its transition system, and we compose together all the parallel composition where there is a rendezvous that is required. And at the end, when we have this transition system, we further reduce it modulo R and return the result. So the problem with we have found, this works in principle, but you have some loss of information when you separate the agents from each other, because then an agent loses the information about what kind of messages it can actually receive from the others. Again, if we think about the Baldi election system, agents can receive this leader variable bound to this leader variable, okay? But when you separate the agents from each other, you can, every agent must assume that it can receive any value for that variable, okay? And this leads to a blow up in the size of the individual transition systems, so we want to fight that. How do we do that? We introduce a very lightweight value analysis that gives us an over-approximation of the values that leader can assume. And this is really, broadly speaking, basically we just take all the assignments in our specification, then we start from an abstraction of the initial state of the system, and then we recursively apply every assignment to every state that we can reach from this abstract initial state until we reach a fixed point. Okay. So this is essentially what we are kind of running the chaos automaton of the assignment in our specification. Okay. And when we reach a fixed point, we merge all the states that we have found so far, and we obtain another approximation of the values that every variable may assume in any execution of our program. And so, again, if we run this algorithm on our specification of the leader election system, we find out that leader actually cannot take any value, but just the ones between 0 and n, where n is the number of nodes. And then we take this information and we plug it back into the LNT program. So what we do, when you have this block where an agent may react to an incoming message, we add a where clause to the receive offers that that correspond to this reception, and we say, okay, but the message you receive must have values that are within the result of our value analysis. So, and this works rather well in practice. So we run some experiments, and we compared this compositional workflow to a previous verification approach that was also based on CADP, but was using a sequential LNT encoding. So the interleaving between agents was resolved by a scheduler that selected an agent and let it perform its own move, and so on and so forth. We have verified a collection of examples written in our language. And for instance, okay, these are some instances of the leader election system. We have a two-phase commit system where the exchange of information happens also on the Stigmergic, and some other, let's say, multi-agent systems with flocks of birds or formation, line-forming agents. What we can see from the results is that essentially the baseline approach is the best one on very small instances because it doesn't have to suffer from the overhead of, splitting the agents and generating all these little transition systems and putting them back together again. But of course, as you can see pretty clearly from the leader election systems, as you increase the number of agents, this baseline approach suffers severely from the state space explosion problem, as especially when you switch from 6 to 7 agents. So you have a massive increase both in the verification time and memory. Whereas the compositional approach is scales rather better in both in time and memory. Then we added a third column, and this is the same workflow, but it's a theoretical computation of what would happen if you run the individual state space generations on different cores rather than sequentially on the same core. So of course you get some benefits when it comes to time, but sometimes you have to pay a price in terms of increased memory consumption. So yeah, another thing that is interesting is that some of these systems we restricted the interleaving of agents so that agents perform their actions in a round-robin fashion. And this is greatly beneficial for the baseline approach, as you can see from the times required to verify the flock system in round-robin versus without round-robin. But in the compositional approach, this is actually quite the opposite. Like it's much more efficient in verifying full interleaved systems, which is interesting because that's what we usually want. Like round robin is kind of a harsh restriction on all the traces that may happen in a real system. So to wrap up, we properties in these collective systems, and compositional verification, as we are shown, can be useful to fight against the state space explosion problem, and especially when we help it with some value analysis to run down the size of individual transition systems for the agents. So, of course, for the future, we want to investigate a better approximation than the one that we have so far. So we could use better abstract domains or a better algorithm that does something a bit smarter than just considering the chaos automaton. And of course, we may want to actually build this parallelized workflow so that we can actually check if our theoretical measurements actually show up in reality. And that's it. And I mean, and there are many other things that we are working on with the language, but yeah, time's up, I guess. So thank you for your attention.
In your parallel model, do you use a shared memory or is it duplicated?
Do you use, sorry, what?
Shared memory?
I mean, the language does support it in principle, but we are not, so far we are not using it. Like, this workflow is just for agents that communicate via these Stigmergic variables. But yeah, there is no shared memory in those systems.
If you come back one slide to your measurement here.
Yeah?
The amount of memory consumed in the parallel setting, is it total or per agent?
No, this is total.
Total, no?
Yeah.
Thank you.
Thank you for the talk. I'm not super familiar with these types of collective systems. Is it typical that temporal logic properties are the types of properties that people would be interested in, or is there something about these systems that people instead would look at different properties?
I mean, it depends on the area of expertise of the specific domain, but typically people are interested in some like emergent features. Like at some point, this kind of nice thing will happen, right? And this is a typical temporal, like liveness property. So we think it's this kind of, model checking is rather good at that. So that's what, they don't call it like a liveness property, of course, but the idea is there somehow.
Yeah, I guess I wondered if the systems would, like the agents you'd want properties that talk about how sub-regions of the agents behave or how they interact and kinds of things that maybe wouldn't be so. I definitely agree that there's this because it's emergent thing, you get this flavor of eventuality, but then the atomic propositions, is it always convenient to describe them this way, or?
Well, sometimes, I know what I kind of, if I got the question right, yes, there are some properties that are a bit more sophisticated, like there are, like in opinion formation system, there is this thing called metastability, where like you are not converging to a consensus or anything, but the values of like people with one opinion versus the other stays more or less the same for some time before you have this phase transition and everything results. And that may be harder to describe by just using state predicates with modalities, and we may want to investigate that in the future. But in principle, it should be describable with a complex enough mu calculus formula, right? I guess.
This your compositional setting kind of reminds me of other kind of instances of compositional model checking, like assume guarantee or rely guarantee or whatever they're calling it these days. And I guess part of your motivation was to be push button, so not wanting to have to write down the invariance on which you're assuming and relying. And I guess it seems to me that this piece where you try to over-approximate the reachable states might be the stand-in for the automatic generation of those invariants. Are there parallels there? And if so, do you think what you're doing could fit into the existing framework of assume guarantee, rely guarantee?
I briefly touched on assume guarantee approaches in the paper, in the related work section. And so far we haven't considered it just because it's not something that this tool supports by default so far. You can define some assumptions and guarantees in the functions, but these are only used in the generation phase of the transition system. They are not used as conditions to the verification. But if this changes, it may be interesting. The thing that we want to understand is if there is a technique to find these assumptions and guarantees that is independent of the particular system that you are verifying. All this is pretty much agnostic of what's going on in the system, the whole workflow. So that's another that we would like to have something like that also for this kind of technique. So.
Yeah, well, I was thinking in particular, like for your example, when you said that the ID has to be like less or equal to n.
Yeah, for example.
That is like an assumed guarantee condition.
Yeah, it is. Yeah. And there are some things that are called in explicit model checking. You have behavioral interfaces, so-called, which are other approaches that can essentially you put them between the transition system and the environment outside, and somehow they can help you prune this behavior in other ways, and they are more powerful because the interfaces are processes themselves, so they can have some kind of temporal behavior. It's not just a static thing like the value analysis. So that could be interesting, but again, it's pretty hard to find something that is generic and is actually effective, like perform some actual pruning that speeds up things in a noticeable manner.
Okay, thanks.
Can you tell us more about what the properties are for these examples?
Oh yeah, I mean, there are all properties of the same, like say, shape as the one I shown in the slides. Sorry for not saying that before. They are all like along every fair execution, this kind of state, a state that satisfies this property, occurs infinitely often.
Okay, let's thank the speaker one more time.